Section 3.3, Applications of Nonlinear Equations. In 3.2, it was almost the same, but it was for linear differential equations. If you haven't seen the recorded video for that section, please do so. And what this section talks about, there's a lot of examples about it. There's a lot of examples about this one. No late homework assignment, please. No late. No. We just go by the syllabus, whatever we have on the syllabus. No late assignments. So one of the examples about where differential equations are used, if they are linear or nonlinear, is with population models. So with population model, what we've seen so far, the rate of growth, dB dt, that's the population growth with respect to time, is proportional to the population itself. And in the previous section, we've seen how to solve this kind of differential equations using separable. And we also covered this back in Calc 2, I think, Calc 2. So one of the mathematicians, he started with a population model other than this one, the dB dt equals kp, because this kind of model didn't work really nice with a very large population. So he came up with a different kind of population. So what he did, population model, he kind of like divided or multiplied both sides by 1 over p, like so. And instead of k, he came up with a minus bp, like so. What is a here? First thing, this side is the rate of growth after dividing by p is the rate of growth per person or individual. That's what the left-hand side gives us. Both a and b are positive numbers. This a represents the birth rate, and this represents the average death rate. So birth rate minus average death rate. It will tell us if it's negative, positive, if the population is increasing or decreasing. And then if we take this model, this equation or differential equation, and multiply both sides by p, we get a minus bp times p. This, what we call it back then, or you can write it as p times a minus bp. I don't know if you remember from calculus, this we call the logistic differential equation. This is called logistic differential equation or logistic equation or function. The question is, how do we solve such differential equation? Who's going to help us to see how do we start solving dB dt equals p times a minus bp? How do we start solving this? What do we use?
Integral.
What is it?
Do we take the integral?
Before we do integral. Bernoulli, is this a Bernoulli one? What is the first step? So Min said separable variables, so use separable first. So separate the variables we have. We can bring the p times a minus bp down and dt up. Then Peter said integrate both sides. How are we going to integrate this one? Does the U sub work? Please participate. You can use the chat at least to say yes or no. Does U-substitution work? Okay, so some said no, it doesn't work. What about, is there another way to do this? Min said fraction decomposition, partial fractions. Okay, partial fraction decomposition. We can do that work on the side. 1 over p times a minus bp. It's a, capital A over b plus capital B over a minus bp. U sub doesn't work. Then we multiply by the least common denominator. We get 1 equals a times, yes, a and b are constants, b times b, like that. That's not a Bernoulli one. So how do we solve this for capital A and capital B? What's the easiest way? Set 1 to 0. Set B equals 0. Yes. We get 1 equals, the second term is gone, AA. So capital A is 1 over small a. What another value for P we can pick here? Yes, thank you, so on. So it's A over B. So this part is gone if you substitute A over B. And the other one is simply A over B like this. So B is, what is it? B over A. So now down here, we can rewrite the 1 over P times A minus BB as A over P, so 1 over A over B plus B over A minus BP. This is the left-hand side, and the right-hand side stays the same. We can split this into two integrals. Take the 1 over A out. Take the other one out. The first one is very easy to find, to calculate, to find this integral. What about this one? What should we do? U sub. Anthony said U sub. So U equals what? The only option is the denominator. Du is negative B dP. So what I need here, we need a negative B dP. So I need the negative, oops. So you multiply by negative B, and you do the same thing here down there in the denominator. So this becomes 1 over A natural log of the absolute value of this minus The p cancel each other. 1 over a. That would be the integral of du over u. Again, natural log of opposite value of u, which is a minus bp, equals t plus a constant. So when they say solve this, what are we trying to solve for? What are you trying to find here? P, yes, the P. So how do you solve for P here? Combine the logs. Yes, first you can multiply by A to kind of clean up the fractions. And someone said combine the logs, natural log of P over A minus BP, like that. What's next? E both sides, exponentiate both sides. You get the opposite value of B over A minus BP, e to the AT plus AC, which can be written e to the AT times e to the AC. You can drop the opposite value by doing plus or minus e to the AC times e to the AT. This is all constant. We can rewrite that constant as, let's call it C1. Then it becomes an algebra part here. From there on, cross multiply AC1 e to the AT. To solve for P, we have to add BC1. PE to the AT equals AC1. We group the terms containing capital P, and then we can factor that one out. And now we can solve it. What can be done with U-substitution? The original equation? Yeah, how can that be done? We're gonna come back to this to finish it up. So if you take U equals A minus BB, then du is negative B dP. How can we finish this up? So if you multiply here by negative b and then negative 1 over p there, so this becomes negative 1 over b. The top is du and the bottom there's a u here. And then what happens to this? Okay, so he solved for b here. A minus u over b, okay. Then what? So we're waiting for Fran to tell us. Do you see, even if you do it this way, that's fine, you tried, that's good, a good trial. But even if you do it this way, you still end up having to use partial fraction decomposition. So please copy this if you haven't done so. So now within this equation, there are two exponential functions. To reduce it down to 1, we can divide each term on the right hand side of the fraction by e to the at. So on the top, it cleans it up. Here, 1 over e to the at, 1 over e to the at, same as e to the negative at. And this cleans up the other one. Some people like to write it AC1 over BC1 plus. They put the e to the negative at on this side, like after BC1. Either one would be fine. So one thing here we don't want to see is the C1. So you can say we do not want C1. And how can we get rid of the C1? Usually it's given the initial condition or the initial population P of 0 means the population at time equals 0. We call P sub 0 will be given to us. So we can take that and use substitution. We substitute. And what do we get? P of 0, that's P naught equals, substitute into this equation, AC1 over BC1 plus e to the 0, which is 1. And what we need to do here is to solve for C1. And then substitute this back into the equation. So how do you solve for C1? We can cross multiply. AC1 is P sub 0 BC1 plus P sub 0 or B naught. So AC1 minus B0 BC1 is B sub 0. Factor C1 out and divide. Now, what we are going to do is take this C1 and substitute it back into the equation that we just found for capital P. So what we're going to do is I'm going to split you using the breakout rooms and work together. Don't just work on your own. Work together. Say, hey, let's do it this way. If you find someone who's not participating, bug them, ask them to do so, to say something, speak up. So are you guys ready? If one student is infected, it was initially infected, how many? How many infected after 6 days? If after 4 days 50 are infected in a population of 1,000, let's say 1,000 students. This is a nice example to find out, let's say, kind of like a prediction here tells us how many do we expect to get infected after 6 days. If we know how many initially were infected and after 4 days how many were, what was the count of the infected students? So to write this, the given down in mathematical symbols, we say at time t, there was X number of students infected. If there was X number of infected students, then there was 1,000 at the total number minus X not infected. Not infected. What else they give us? They said if one student is infected initially, so this means X of 0 at time equals 0 is 1, only one person. After 4 days, so X of 4, t equals 4, there were 50 infected. It says the rate. What's the rate? The rate is dx dt, that's the rate, at which the flu spreads is proportional. Proportional means is constant times, both for infected and not infected. So both of them, not infected. So the infected is x and not infected is 100 minus x. So that's how we translate that into an equation like this, specifically the differential equation. And how do we know we're going to use the one that we just learned in this section, this model that we have? Well, let's see, what was the model that we gave you? It was dp dt equals p times a minus bp. See, it seems now if I compare them or try to match them, so here the x matches with the p. So if I have a k there and I multiply it inside, that gives me, it's 1,000, not 100, 1,000 k minus kx. So comparing these two together, what do we get? What is a here? A is 1,000 k. What is b here? See if you compare this one and this one. B is k. And what is p sub 0, or b in the front? It's 1. P sub 0, that's the initial one because there was only one infected student. And why do we need this? What do we need this for? Well, because if you look back at the solution, the formula here in the box, to be able to solve this, we need a, b, p0, and small b. We need them to substitute them in. So instead of P equals, we're going to have x equals, x or x of t is given the formula we derived was a p0 or p naught b naught plus a minus b naught times e negative at. And now we're going to see what is given and how do we finish this up. What are we required to find here? What are we trying to do? Who's going to tell us what we're trying to find? T plus 4? Yes, you can talk.
The effective rate first, and then the total number of effective students after 6 days. Like the final answer.
Yeah, so when t equals 4, right? Yes, thank you. So somebody really said, like a couple of people said, we need to find x of 6. How do you find x of 6? So that's what we are going to do now. The first step is x of t equals, substitute the information that we know. A is 1000k. P sub 0 is 1. Small b is k. B sub 0 is 1. A is 1000k minus b is k. B sub 0 is 1. E negative. A is 1000k times t. We can simplify it first, write in a more simplified form. That's 1000k, that's a k. This is 1000 minus k, 999 k. Keep this the same. We can divide by k, top and bottom, so we get 1000 divided by 1 plus 999, e negative 1000 kt. So notice something. If you try to substitute 6 for t, that's not going to give you an answer because we don't know what k is. So this k, we don't know it. So how do we find k? First, we need to find k, and then we find x of 6. Who's gonna?
We set t as 4.
T of 4. So okay, so I think Albert was talking. So he said use this given. So we already used the first one, but we haven't used this yet. X of 4 is 50. So we substitute x t4. This is 50. It's 1000. 1 plus 999 e negative 1000 k, and t is 4. If you cancel 0 with 0 by 5 1 520, 1 plus 999 e negative 4000 k equals 20. Now we subtract 1 on both sides and divide by 999, then natural log both sides.
Professor, how'd you get 4000k?
4000? 4 times 1000. Do you see it?
Yeah,
1000.
sorry, my bad.
So now we can bring the negative 4000k down. Natural log of e is 1. And then natural log of 19 over 999. Then k equals negative 1 over 4000. Natural log of 19999. If you put that in the calculator, I got about 0.3099.
So Professor, when you're doing this, are you allowing only 2 sigfigs for the K?
Are we allowing, what is it?
Are you allowing 2 significant figures?
Yeah, it's fine. Yep. And where were you? You did not join the breakout rooms.
I was in the restroom. Sorry about that.
So now after we found the K, the value of K, we are going to put it back into the equation x of t, 1000, what was it, 1 plus 999 e negative 1000 k t. So now it's ready for x of 6. So x of 6 is 1000 divided by 1 plus 999 e negative. You can multiply that 1000 right away, 0.99, and t is 6. And if you put that in the calculator, I get about 276 students. So this will help us to predict the number of students, of infected students on day 6, based on the given information. Any questions about this?
Professor, can we do one more example, please?
Oh no, it's gonna take forever. You know,
Professor?
you can go to the textbook and do the problems. This is not like solve like an easy algebra problem, because if I want to give you another example, I just change the numbers. So someone else has a question? Will we need to use a calculator? Yeah, to do this, something like this, you need a calculator.
Professor?
Yes.
So, the original equation, the original differential equation that we solved,
Yeah.
why couldn't you solve that as a Bernoulli equation?
Why can't we solve using, what is it?
Bernoulli.
So let's recall what Bernoulli differential equation is. Does anyone remember?
dy dx. Oh, go ahead. Oh yeah, sorry. Dy dx plus x, or a function of x times y equals a function of x times y to the n.
And was it in that form?
You can make it into that form.
And there is a y in there? There's nothing missing?
I mean, the p, it's dp dt instead.
And there is a p in there?
Yeah, so you would get PA minus BP squared, and then you bring the PA to the other side, so you have dP dt minus AP equals negative BP squared.
Before we continue,